Okay, so basically the median, so the exam had 120 points on it. You are only being graded out of 100. So for example, if your score was, say, 84 out of 100, 84 being the median, I'm sorry, if your score was 84 out of 120, it's really 84 out of 100. So your score for the exam was really 84%. If you got more than 100, which a number of people did, then you're ahead of the game. Okay, it's an A plus according to the way I grade. So the curve was in the fact that I had 20 extra points on the exam. So there is no curve, therefore, for the grade. 90 to 100 is an A, 100 plus is an A plus, 80 to 90 is a B, 70 to 80 is a C, 60 to 70 is a D, and anything below 60 is an F. Okay? For the most part, I noticed in handing stuff back, most of you seem to be 80 or above, so probably not really talking to you when I say this, but if you did score below 70, you're going to have to put more work into this course because the material gets tougher from here. A lot of what we were doing was review material in the first few weeks of the course, stuff that you'd seen in CS 102 plus some additional material. But from here on out, it's all new stuff. And that may mean having to go back and memorize the notes because the questions from this exam were essentially all taken from either notes or lectures. You could have memorized most of this stuff. Like question 9 on Moonglow, even though it said Moonglow, we did a problem like that early in the course in class where we had you read in numbers and words and print out first the numbers and then the words. So if you'd simply memorize that particular program, you could have essentially just dumped it on the test with a few modifications. So it may mean, as I said, more memorization work. It definitely is probably going to mean going over the notes outside of class, and when it says you need to perhaps work this out on your own, you really need to try to work it out on your own. So those are some of my hints. Like I said, for the most part, the exams I handed back and people took look pretty good in here, so I doubt I'm saying a lot that's new to most of you. As I said, the median was 84. That was right in the middle of things, so that's good. Please go over the video that went with the exam. The two problems that people most missed were surprising. It was hexadecimal arithmetic, which was question 1, and question 4 on bit manipulation. Almost no one got it. Okay, so we're probably going to have a Blackboard quiz on that at some point. Those are two important concepts that you need to know. And I'm not going over them. I went over them in the video lecture with the exam, but there's probably going to be a Blackboard quiz on those two topics that are going to have some count toward your final grade because it's important that you know how to do that. So, Mark.
For the people who took it on Blackboard, will we be getting back the exam, or how is that work?
No, you should have comments on Blackboard. If you don't, then we need to talk. Is that true for everyone on Blackboard that you haven't seen your test comments?
Yeah.
Okay. I'm going to have to figure that out then because there's comments and the like. So, Alan, do you know? Okay. I'll look into that because the comments are there. And do you at least have your scores?
Yeah.
Okay. So I'll look into why the comments aren't showing up yet. Okay. Okay, so no one who took a Blackboard exam has comments. Is that correct? Okay. We'll figure that out. Okay, so we are going to finish up pointers today, and we are going to be moving on then into lists and double-ended queues, plus some warnings about vectors, why they are often inefficient, and why you should not be using them in many situations. So first thing I wanted to do is just to finish up with pointers, and I wanted to go over a couple of the examples that Dr. Planck gave in his notes. The first one was his example with vectors. Okay, so he had a number of vectors that he declared. So he had I'm going to write it out. He did it as he used type defs. I'm going to write them out. So he had a vector that was a vector of ints, and that was IV. Then he had a vector of ints, which was a pointer to it. And he had a vector that was a vector of ints star. So this is a vector of pointers. So this is, first of all, a vector of pointers that you see there. Okay, you know that because of the star at the end. And then what kind of pointer is it? Each pointer is a pointer to a vector of ints. So what this is, this IVPP, if you had several entries, it would look like this. So it would be a vector, say up to whatever, and each one would be a pointer to a vector of integers, not necessarily the same size. Okay, so that's what IVPP is. It's a vector. So this is IVP right here. This is IVPP, and it is a vector of pointers. Each entry points to an integer vector. Okay, so that's what that is. Any questions about that? Okay, so I'm going to erase it. And he also had a class, which was earlier, that he called VP. He was going to make it into a vector pointer. Public vector int IV. Okay, so this was really up on top. And then he had a pointer to VP. Okay, so that was his five declarations. And then he did a whole bunch of operations. So the first thing he did was he assigned IV a set of random numbers. Okay, actually let's go back here, extend the page. You can't, well, we're just going to have to go to a new page. So he gives IV 10 random numbers. Okay, so IV looks something like this now. IV, I'm not going to print all the random numbers. Okay, see if he did. So he has a bunch, 18, 87, 91, 66. The point is he assigned it a bunch of random numbers. Okay, the next thing that he did was he set IVP. So that was first thing. Number two, he set IVP, the pointer, to be equal to the address of IV. Okay, so what this meant is that IVP now has a pointer. Well, I shouldn't do it like that because that makes it look like it's into the middle of it, and it's not. Okay, so we'll do it like this. It now has a pointer to IV. Okay, so IV has 1887, blah, blah, blah. And we now have IVP as a pointer to it. And then the next thing he did was he printed out the contents of IVP. So he essentially said for I equals 0 to, again, we're using pseudocode, IVP. And remember, when you have an object, you use the arrow, and he printed IVP at I. Now, can anyone tell me why he didn't do this? Print IVP I like that.
IVP is a pointer.
IVP is a pointer, and if he's doing it like that, he's treating it as though IVP is an array. He's really what C++ will think is that you really have an array of pointers, and when you say, for example, IVP2, it will think you have a pointer to some integer vector. It's not going to be the second entry in IV. It will be off somewhere in some other vector. So that's why he had to say IVP arrow at I to get at the pointer. So the pointer was to IV. This is what the arrow operator does, and then at I returns the ith entry. Okay? Questions about that? Okay, so then his third operation was to resize. He says IVP resize 4. Okay, so what that does is it goes to the vector to which IVP points and resizes it so that it has only 4 elements. In other words, it eliminated the last 6 elements. So now we're down to a vector that has only 4 elements, and IV now has only 4 elements in it. Okay, so this is showing you how you can reference objects through pointers and manipulate those objects via pointers. Okay. So next, step 4, he sets IVPP, which was our vector of pointers, he sets that to be equal to a new vector of int star. Okay, and he had to do that because if you go back and look at the definition for IVP, it was a pointer. So before you can do anything with that pointer, hopefully you learned one of the things in lab yesterday with the problems is you have to initialize it. So we're assigning it a new piece of memory from the heap. So it's giving us a vector which currently has what size? How big is that vector? 0. Has 0 size at this point. Okay, so right now IVPP points to a vector, but I'm just going to kind of look like that. It has 0 size. Okay, and the first thing we do 2 pushbacks on it. So we say IVPP pushback, IVP, and then we repeat it, IVPP pushback, IVP, like that. So if we go back and look at the previous slide, we see that IVP is a pointer to IV. Okay, so if we actually had our memory diagram, we might have, here's IV at, say, location 1000, and here is IVP at location 1004, and it has a pointer to 1000. Okay, so when we do IVP pushback IVP, what we're really doing is creating a vector with two elements, each of which has the memory address 1000 in it. Okay, because when we pushed IVP had the memory address 0x1000. And what is 0x1000? You can see it is a pointer to the vector IV. Okay, so now he has two pointers to that thing, and what he does is he does an iteration. So at step 5, he steps through. He has for I equals 0, I less than IVPP size, I plus plus, and he is going to print out the contents. So he first sets IVP equal to IVPP at I, and then he iterates through IVPP. And he prints IVP at J. Okay, so what does this do? Okay, so this step with I0, we set IVP equal to IVPP at 0. What is IVP at 0? It's 0x1000. So we're actually setting IVP to be the address of IV. So you can see that when we iterate through this loop, all we're doing is really iterating through the IV vector and printing it out. Okay, so what this is really doing, this prints the IV vector, the contents. Okay. When we go through and increment I to 1, what gets assigned to IVP? Sarah, what gets assigned to IVP? Second time through with I equal 1. Okay, so second time through, what is going to be the result of this assignment right here? With I equal 1, what gets assigned to IVP? Okay, so why do you think it's 1004?
So the pointer is getting the, I guess it'd be 1000 because that's the memory.
Very good. So it's really 0x1000 because I is equal to 1. And if we look up here, IVPP1 is 0x1000. Okay, so it's really getting 0x1000. So the second time through, we're again printing the contents of the IV vector. So he's just printing out the IV vector twice. Okay, is that clear? Yes.
Aren't you just like assigning it to itself? That's what I thought when I was looking at this.
When you said, okay, when you say assigning, assigning, looks like you're assigning IVP to itself. Yeah, it's kind of unfortunate that that's what's going on here. Maybe would have made, it maybe wouldn't have seemed quite so useless if we had had a few more variables here. He was trying to keep the number of variables to a minimum to avoid getting it all confusing. So, but you're right. It is, in effect, just assigning its value back to itself. But what he's trying to show you is he has multiple pointers right now to the same vector. He actually has three, at this point he has 3 pointers to that vector. He has 1 pointer here at IVP. He has 2 more here in the IVPP vector. So he really has 3 different pointers at this point. So you're right. It's all it's doing is assigning back. I could have, or he could have, declared another pointer variable, and then it wouldn't have looked like he was just assigning it straight back in. Okay. Other questions? Okay. So the last thing he did is he sets VP equals new VP. And if we go back and look at VP, you see that VP is a class containing a public member. The one public member is a vector of ints. So he is assigning, he gets a new object, so VP is now a pointer to a object. Okay, this was capital VP. So this is a capital VP class. This is lowercase VP. Probably would be better if we had used different names. So to make it clear, I'm going to say this is a VP pointer. So it now points to a VP object which has exactly one thing, which is an empty IV vector. Okay, so the first thing he does is he assigns VP pointer IV dot pushback. He does it 10 times. So for I equals 0 to 9, he pushes back a random number. And then he goes through and he prints them out. So then for I equals, this should be an equal sign, 0 to 9, he prints VP pointer IV I. And the reason for him showing you this way is this is Dr. Planck's preferred way of printing out vectors that have pointers to them, because he can then use the subscript notation rather than using the at notation. Okay, I think both approaches have clunkiness associated with them, so I don't care which you do. Okay, the previous approach with at has the advantage that it will segfault, or not segfault, it will throw an exception if your subscripts are out of bounds, which I think is helpful, because a lot of you still are having issues with, I'm getting a segfault, I'm not sure why. If you use at, it makes it clear when you get the exception that it is due to a vector. And as we move into pointers, you're now going to have a second source of segfaults. Up to now, you've had really only one source of segfaults. If you had a segfault, you could pretty much safely assume that you had a vector subscript out of bounds. But going forward, there's going to be 2 potential causes of a segfault. One is going to be a vector subscript out of bounds, and one is going to be a dangling pointer, okay, or an uninitialized pointer. So if you get in the habit of using at, then at least when you have an out-of-bounds subscript, you will have an exception thrown, and you will know that it was associated with a vector as opposed to being a problem with a pointer. Okay, so while Dr. Planck does like this notation because he's able to use the vector notation, I think that when you're writing your programs, you're actually going to be probably better served if you use this at notation instead. Okay, is that clear? So I would try to get in the habit of using @. It will make your debugging lives a lot easier. Okay? We good? Okay, so it's your turn. I could now go through Dr. Planck's next example, but if I did, it's not really, you're just going to be following along with me without really doing anything, and I don't think that's as helpful as making you try to do it first. So his next thing, which hopefully you read through it already, if you didn't, you're going to have to try to come up to speed quickly, is he went through an example where the people, you're being hired to write a knockoff Facebook, and you have this class person that stores some information, a name, the person's mood, if they're in a relationship with another person, and a vector of pointers to their friends. And then he has shown you some code, and he then has gone through it, and he is going to do the following set of commands. What I want you to do now for about 15 minutes is try to simulate these commands, and what I want you to do is try to figure out what the pointers look like. So, for example, I'll give you a hint. Start, new person Scarlett O'Hara. If you look in his code at new person, you see that new person, it tries to find the person in the hash table, and if it is already there, it prints unsuccessful, but if it fails to find the person, then it inserts it into the hash table, and it's going to create an instance of it. And here he has his find person, and you can see that when it does the add, it actually creates a new person, and it actually assigns initial values to them. So with my first thing here, Scarlett O'Hara, it's going to end up, you don't have to know exactly which values in the hash table it goes to, so don't try to figure out what it hashes to. That's irrelevant. But just create, like pretend, just assign places where Scarlett O'Hara might go. So now you have a pointer to a vector, so he's using separate chaining. So he has a vector. Let's say it goes into entry 2. And now his first vector points to a person whose name is Scarlett O'Hara, Scarlett O, whose mood is neutral. Okay, and who has some other attributes. So what I want you to do is go through this set of commands and try to simulate his code. Okay, if you need some help, well, he's gone through it to himself. Okay, but what I want you to do is, as I said, try to do it on your own. You can do it with a partner because it'll be you'll get a lot more out of it if you try it yourself. Okay, if you're stuck, raise your hand. Alan and I can come around and help you and try to get started. Like I say, feel free to use the assistance of a friend or two on this. And I'm going to give you to about 10:30, and then we'll go over how he got this picture, because this picture is all over the place, and I want to see if you can figure out how he derived it. Okay, so the picture, the end result is down there. The question is, can you derive that picture? Okay, and again, you're using this set of commands. You will need a laptop. And you will probably need a piece of paper. Okay, if you don't have a piece of paper, I have a few scrap pieces. So anyone who needs a piece of paper, I have some scrap pieces. Does anyone need paper? Anyone else see a scrap piece of paper? Okay, so I'm going to go over this. I know many of you haven't yet finished it, but hopefully by at least taking a look at it, you've had a chance to puzzle over it for a moment and try to get an idea of what's going on. So let's now take a look at how we're getting this diagram. So the first thing we're doing is we're creating a new person, Scarlett O'Hara. Okay? And if you go to the creation of a new person, which is up in Find, you'll see that we create a new person, so we get a pointer P, and then we assign the name to its name field, the mood neutral to its mood field, a null pointer to its in relationship because it doesn't yet have a relationship, and then we put it into the appropriate entry in the hash table. Now, I got a good question about why does it sometimes use an arrow and why are we sometimes using a dot? So we use an arrow when we have a pointer to an object, and we use a dot when we have the object itself. Okay, so in this case, if you look at what HT is, okay, you can see that it's a vector, and what it really is a vector, and each element is a vector of person pointers. That's what HT is. Okay, so when you first create HT, it looks like each vector that is in it is empty. So it's kind of like nothing. I'm just going to do it like this. The vectors are empty. Okay, so it has a vector, but each of them are empty. Okay, when it does a pushback, like right here, let's say it did a pushback 2, now this has a vector with one element, and it has a pointer to a person, which in this case his name is Scarlett O'Hara. So when he says HT of 2, he has an object. What he has is this object right here, which is a vector of person star. Okay, that's what this declaration right here says, is that each entry is a vector of person star. There's no pointer. That's not a pointer. Okay, to make it a pointer, I would have had to have done this. I would have to say vector person star, and then after it, I put a star. Now, this would be a pointer to a vector of person stars. But the way I wrote it here, I just have a vector of person stars. So when I say HT2, I have an object. That's why I say dot. But if I say HT2, 0, now what I'm getting is a person star. That's a pointer to an object. And that's why here you see the arrow, because now I have a person star pointer, and I need to reference an object to which I have a pointer using an arrow. This will take some getting used to. It's not going to be obvious at first. You're going to get a lot of compile errors. So if you're frustrated at first, try to keep working through it. It is frustrating, and you'll just have to get used to the difference between the two. So questions about this? Okay, so when we're done with this first step, you have right here, he put it into location 7, you have this blue pointer to Scarlett O'Hara. And the same thing happens with the remaining new persons, Rhett Butler, Ashley Wilkes, and Melanie Hamilton. They each go into a certain part of the hash table. So Melanie went into location 8, and we have Ashley Wilkes going into location 7. You can see that Ashley and Melanie collided. So that's why here in entry 8 of our hash table we have a vector of size 2 right now, because Ashley Wilkes went in first, then Melanie Hamilton was added later, and therefore she is the second entry in that array. So that's how we get the set of blue pointers, okay, which he labels as coming from the hash table. So the blue pointers come from, creating a new person. Okay, so he then, so you have to get rid of that. The next thing he did was he added some friends. So he added Melanie Hamilton as a friend to Scarlett O'Hara. So Melanie Hamilton is Scarlett O'Hara's friend. So if we look at the code for add friend, you see he got the names of the two people. Then he checked to make sure that they were both in the table, because it's no good to make a friend with a non-existent person. So he got the pointers to the two people. So P right now is a pointer to to Scarlett O'Hara, and P2 is a pointer to Melanie Hamilton. Okay, so if he failed to find either person, he says he was unsuccessful. Otherwise, you see that he says he goes to P's friends vector, which is Scarlett O'Hara, and he does a pushback on with P2, which is a pointer to Melanie Hamilton. So if we go down and look at our final picture, you can see that Scarlett O'Hara has a friend. Her first friend is a pointer to Melanie Hamilton, right here. So that's what that pushback did. Okay, so the green arrows denote friends. And if you look at the remaining friend relationships, let's look at Scarlett got a second friend. Scarlett also had a friend, Ashley Wilkes. So down here, you see that the second pointer goes to Ashley Wilkes. And then she added a friend, Melanie Hamilton added Scarlett as a friend. So down here, Melanie Hamilton has a single friend, which points to Scarlett O'Hara. And you see Ashley Wilkes and Rhett Butler, neither of them have friends, so their vectors are empty. They have 0 size. So questions about that one? Okay, and those are, okay, then we have in relationship. That's the last thing he did. So he's going to put Rhett Butler in a relationship with Scarlett O'Hara. So Rhett thinks he has a relationship with Scarlett O'Hara. Okay, Scarlett O'Hara would have to indicate she had a relationship back for it to be a two-way. So if we go and look at the in relationship, Okay? We get both people, so that's what we're doing there. So in this case, P is a pointer to Rhett Butler. And P2 is a pointer to Scarlett O'Hara. Again, if it's unsuccessful, he prints, if neither one, or if either one is not found, he prints unsuccessful. Otherwise, he makes Rhett Butler, in this case, P's in relationship field point. So his in relationship field, Rhett Butler's in relationship field, now points to Scarlett O'Hara. Okay, which if we go down here, we see is exactly what happens. We see that Rhett Butler has a pointer from its in relationship field, and it goes up and points to Scarlett O'Hara. Okay, and there it's not a vector, it's a single pointer, so you can only be in a relationship with one person. So he also had, if you see up here, he also put Scarlett O'Hara, said she had a relationship with Rhett Butler. Therefore, down here you also see an arrow from Scarlett O'Hara to Rhett Butler. So that is how those diagrams get constructed. Okay, questions about this? Guess what you should expect to see on your second midterm? A question that's very similar to something like this. Very similar, okay? So instead of maybe a question 10 where you were tracing code in a vector, you now might be tracing code that's creating these kinds of pointers between things. Okay, so we're good with this? Okay, excellent. Okay, so we have a little time left, which gives us the time to give you a nice little introduction to Qs and DQs. And, I'm sorry, not to Qs, to lists, iterators, bad vector usage, and DQs. And we really don't need a full 2 lectures for them. So first of all, lists are going to be a new type of data structure. And you are very familiar with lists. You make a grocery list to go and get groceries. You make a to-do list. Okay, and you know how things go with groceries. You say, okay, I want to get oranges, I need milk, I need soup, I need eggs. So you have a list, and then maybe as you go to the supermarket, you start crossing things off. So you get the milk, so you cross it off. And then you get the soup, and you cross it off. So what you're doing is you're doing deletions in the middle of your list. Okay? Something we haven't really seen before is trying to delete elements that are in the middle. Okay? Now, there's also lists where you want to add things in the middle. A good example of that is email. Okay? Email doesn't always arrive in the order that you would expect. Okay? You might think, well, I'll always put my next email message at the very end of the list. But let's say that, as I'm doing here, I organize my list by date and time of arrival. And sometimes email comes in delayed, right? Maybe when I send you an email, the email server is down, or maybe connections are slow, and I get an email from saying Smiley, who's my dog, and it comes in maybe at 8:02 a.m. Well, I don't want Smiley's email being put at the top of the list because that's not its order. I want Smiley to be put right there at 8:02 a.m. So I want also the ability to be able to insert elements into the middle of a list. Okay? Or as another example, here you might have a to-do list and you keep it in the order that you're going to do it. So I need to go to Home Depot. From Home Depot, I need to go to the grocery store, to Kroger's. Then I need to go to the post office. And then maybe my wife, as I go out the door, says, ooh, you need to go to the library for me. And it's like, oh, before I go to the post office, but before Kroger's, I need to go to the library. So I want to insert library. So with lists, we have a couple operations that we really don't want you to do with vectors, which is to insert into the middle of a list or to delete from the middle of a list. We're going to see that really the only place that you should be inserting an element into a vector is at the end of a vector. So if you want to be able to insert into the middle of something or to delete into the middle of something like a mail server does, then you need to use something called a list. It's more efficient. Okay, so a list, conceptually, this is what a list looks like in memory. It has a series of pointers. So we might have oranges, milk, eggs. I know it's not in the same order as before, soup. Okay, so this one might actually, if you looked at it, you might have class list node. So you'll hear us, you have to get used to hearing us say node. You might have class list node, and you might have, say, public for the time being, even though we don't normally want you doing this. You might have string item, and then list node next, and it's a pointer. So what you have here is next is a pointer to the next list node in your list. So for example, orange points to milk's list node, milk points to eggs list node, and so on. Okay, so it is fairly easy to add things to these lists. Let's say I wanted to add, I'm in milk, so I want to get yogurt. Let's say I'm doing it in order. So I can go to milk and I can create a new yogurt, and then I can reroute milk so it points to yogurt, and then make yogurt point to eggs. So it's a fairly simple insertion into this list. And similarly, if I want to delete something, let's say I just picked up eggs, I can first make yogurt. You can see that after we delete eggs, we want yogurt to point to what? What should yogurt point to after we delete eggs? Soup. So we first make yogurt point to whatever eggs point it to. Then we can delete eggs. Okay? Very simple. From yesterday, can someone tell me what is the danger? So step 1 was to make yogurt point to soup, and step 2 was to delete eggs. Okay? What happens, potentially, if I reverse it? What if I first delete eggs? I lost the object. Okay, I have no way, potentially, of getting any more to this pointer to soup. Now, it may still work, but there's no guarantees because I returned eggs, I deleted it. It's potentially gone. What some memory allocators do in this case is they wipe the memory. And so if I now tried to get access to eggs pointer to soup, I would get a segfault. So it's very important that the order that you first rearrange your pointers then you do the deletion. Now we're going to get into this in much more detail in another couple weeks, not till the beginning of, well, really the middle of March when we get into this. So I'm not going to get into details right now. Right now, we're going to be showing you just how to use these creatures. Okay? So that's a list. Allows you to insert into the middle of it, delete from the middle of it. Another thing we're going to talk about is something called a double-ended queue, or DQ. Okay, it stands for double-ended queue. So you're used to double-ended queues. They're called lines. Okay, a double-ended queue looks like this. Think of a line, like at the grocery store. So where do you come into the line at a grocery store? If this is the line, do we get to come in at location 0 in the line? What happens if we try to come in at location 0? A lot of nasty looks, right? Maybe some angry words exchanged because we're ditching the line. Where do we come in? We come in at 5, so we actually come in at 6. We add ourselves there. And when the customer representative serves someone, where do they serve someone from? Back of the line? No. From the front of the line. So they do the person at location 0. So this is what we call a double-ended queue. Yeah, we have to use jargon for it. We can't call it a line. We call it a double-ended queue. So it means in a double-ended queue, we add elements to the back of the queue. So at least queue is a fancy word for line, right? If you go and look it up in the dictionary, you will find that one of the things for queue is a line. And then that's why it's called queue. And then we remove elements from the front of the queue. Mm-hmm. That's true. Okay. Good point. Thank you, Alan. In fact, I am describing a queue. So we're starting with, this is actually just a regular queue. Thank you. Okay, so that's a regular queue. And then, in fact, a double-ended queue is one where we can, so that's a regular queue. So actually, I want to continue with this for a moment because I do want to. So, occasionally someone leaves a line, right? They get disgusted or they need to go for another item, right? So you also have to be able to sometimes remove elements from the middle. But that's rare. You don't often see people leave from the middle. So we try to make these operations efficient. This operation may be inefficient. Okay, so whereas in a list, we want it be able to insert into the middle of the list and delete from the middle of the list. That should be efficient. With a queue, we want adding elements to the back of the queue and the front of the queue to be efficient. We are less concerned about the efficiency of removing elements from the middle. That can be inefficient. In fact, often is. Now, a double-ended queue is, in fact, one that allows you to efficiently add items either to the front or the back. So it allows items to be efficiently added to either front or back. And it allows items to be efficiently delete it. From front or back. And it's still inefficient to delete or add in the middle. Okay, double-ended queues use tricks. They're typically implemented with vectors of vectors, and we're not going to get into their implementation, but behave, we'll say they behave like vectors. They're actually using, if you look into the STL implementation for them, you'll see that they use tricks and complicated tricks. So we are not going to talk about how the STL actually implements them, but know that double-ended queues behave like vectors, but they allow you to efficiently add to either the front or the back. One more thing and then I'm done. Vectors, and you should write this down because again I love to test on it. Vectors allow you to efficiently add or remove from the back okay, inefficient to add, remove at the front. That's why those of you who on the test attempted to add or remove items on the padding vector got maybe a point or two off is because it's very inefficient to add or remove items from the front of a vector, and it's also very inefficient to add or remove items from the middle of a vector. Okay, so we have three different structures which we'll talk a bit more about on Tuesday. Vectors, which are only efficient to add to at the back and remove to from at the back. Double-ended queues, where it's efficient to add either to the back or the front and to remove from the back or the front. And lists, where it is, I guess I didn't write it down, but where it's efficient to actually add anywhere, and it's also efficient to delete anywhere in a list. Although vectors and dequeues are going to be more efficient at the ends. So we will get into this with some examples on Tuesday.